Hey guys, welcome to Nephro Nook. Today I'm going to go over how to analyze an acid-base disorder. Let's get started. Let's start with a metabolic acidosis. So your pH here is low. That, by the way, a low pH just means acidemia. If you have if you have an acidosis, that really is just a disorder behind it. So you can have an acidemia with a metabolic acidosis or acidemia respiratory acidosis. So metabolic acidosis, low pH, low bicarb. And let's go over a little bit more how I methodically analyze metabolic acidosis. My first question, actually I'll put this over here. My first question is there an additional respiratory acidosis or alkalosis? My second question is, what is causing the acidosis, the metabolic acidosis? As in, is it specifically a loss of bicarb? Or additional anion? And the third question I answer is there an additional metabolic acidosis or alkalosis? You might wonder why I don't just say, is there additional, like is my first step, is there additional respiratory process? And my second step, is there additional metabolic process? I have to do number 2 in order to get to the answer to number 3. So let's talk a little more in detail into each of these. Let's first talk about how you can tell if there's an additional respiratory acidosis or alkalosis. This is what the Winters formula tells you. A lot of people see the Winters formula as a way to see if there is appropriate respiratory compensation. I don't like that, because how many times do you really have just one pure metabolic acidosis and then you say, oh, and they have inadequate respiratory compensation? Especially in the ICU, you'll have a patient coming in with a metabolic acidosis, maybe from a lactic acidosis. They're also intubated, so their ventilator is also kind of confounding things, or maybe they're just a bad COPD or at baseline, so they also have a respiratory acidosis. So don't think of Winters formula as a way to figure out about compensation. Think of it as a way to figure out if there's an additional respiratory acidosis or alkalosis. Also, I don't like the term compensation. I think it just kind of clouds everything. You could really just have multiple acid-base disorders going on. So additional respiratory acidosis or alkalosis, I'm going to use Winters formula to tell us the answer to that. So what is Winters formula? This tells you that the expected PCO2 is 1.5 times the bicarb plus 8 with wiggle room of about plus or minus 2. So suppose you have a patient with a low pH, a bicarb of 10, and a PCO2 of 30. How do I tell here if there's an additional respiratory acidosis or alkalosis? Well, I use my Winters formula. So here I say my expected PCO2 is 1.5 times the bicarb, which is 10, plus 8 with wiggle room. So that's 15 plus 8 with wiggle room, or 23. So I said that my expected PCO2 is 21 to 25. My actual PCO2 is higher than that, it's 30. Remember, a high PCO2 indicates a respiratory acidosis. So in this situation, I have a metabolic acidosis and an additional respiratory acidosis. So let's put that in here. So additional respiratory acidosis or alkalosis, use Winters formula. Let's go to step number 2. what is causing your metabolic acidosis? Is it a loss of bicarb or an additional anion that is essentially displacing your bicarb? Additional anion. How do I know the answer to this? So little hint, think of this as an additional unmeasured anion. This is where the anion gap comes in. If you have an elevated anion gap, your metabolic acidosis is due to an additional unmeasured or additional anion. If it's just a loss of bicarb, that's a normal anion gap metabolic acidosis. So this is your anion gap. That tells you the answer to this. What's the calculation for your anion gap? It's the cations minus the anions. Notice that potassium isn't one of the cations here. There's two reasons for that. One is that it's primarily an intracellular cation, so it doesn't really play that as much into that extracellular pH. When you're measuring any labs, really, that's all extracellular. It's really hard to tell what's going on inside the cell. The second thing is that actually, I believe in Europe, they do use potassium as part of this calculation. So their cutoffs for anion gap are a little bit different. Oh, I guess I'm assuming you guys are all in the US. Well, if you're in Europe, maybe your calculation is a little bit different. So their anion gap cutoff is about 4 higher than what ours is. So it's more about like 14 to 16. So you get your sodium minus bicarb minus chlorides. Normal anion gap is about 10 to 12. I told you though that your cations should balance the anions. So why isn't your anion gap just 0? What accounts for those additional anions that are in that anion gap? What accounts for that 10? So what accounts for those 10 anions is primarily your albumin. So 10 is your albumin. That's the negatively charged protein really contributing to everything. Each albumin has a charge of negative 2.5. And you'll see where I'm going with this in a second. How much albumin is normally in the body? Normal albumin is 4. So if you have 4 albumin, a concentration of 4 albumin, and each of them is 2.5, multiply 4 by 2.5, and that gets you the 10, the negative 10 charge that is here in your anion gap. The reason I am pointing this out is that this assumes then, if in your anion gap calculation that you have an albumin of 4, if you're saying your normal anion gap is 10, that's assuming that your albumin is 4. What if it's lower than 4? What if you look at your albumin and your patient's albumin is actually 3? So if your patient's albumin is actually 3, and you get an anion gap, you calculate your anion gap and it's 10, well, you know that all 10 of it can't be from that albumin because your albumin is only 3. Multiply the 3 by 2.5, and that's only what, 7.5. So what's the rest of the 2.5? That's got to be your additional unmeasured anions. So really, in that situation, you do have additional unmeasured ions. All of this is to say that you need to correct your anion gap for your serum albumin. So every time so you could do it one of 2 ways. I'll tell you the way that makes sense first, and then I'll tell you the way that you can actually do it in practice so you don't have to think through it each time. So if your albumin is 3, then you know that all 10 of it is not due to the albumin. You know that 2.5 of it's got to be due to something else. You could think of it that way. Or the other way that we really do it more in practice is that we just still say normal anion gap is 10, in that if you have a high anion gap, that's the anion gap metabolic acidosis. So the way you can work around that is say, every time my albumin goes down by 1, just increase your anion gap by 2.5. It's not that it's really just increasing anion gap by 2.5. It's just saying that now, like instead of thinking, and now essentially if you get anion gap of, how would I say this? Now if your albumin is lower, like as in, I'm gonna have to refilm this because I started saying this, now my cat's in the video, whatever, we're moving on. So every time your albumin goes down by 1, just add 2.5 to the anion gap, because now you look at this patient, you get anion gap calculation of 12.5, then you're like, okay, it's an elevated anion gap. So every time your albumin goes down by 1, increase your gap by 2.5. So if your albumin is 3, you calculate so you get a 10, actually you have to increase, add 2.5 to the 10. So albumin, suppose your albumin is 2, so it went down from 4 to 2 by 2. Increase your anion gap, not just by 2.5, now by 5. So you get this calculation, whatever you do for the sodium minus bicarbonate chloride, whatever number you get, just add 5 to that. And so that's how you know that there's an additional and unmeasured anion. Get my real eraser. I have no idea what that is. All right, we're getting the real eraser. So we went over step number 2. The cause is are you of your metabolic acidosis? Are you losing bicarb, or are you adding an unmeasured anion? And remember to correct your anion gap for your albumin. Every time your gap goes down by, or albumin goes down by 1, increase 2.5 to your gap to account for that loss of albumin, which each albumin charge is negative 2.5. So let's go a little bit more into what causes your metabolic acidosis, even though you don't necessarily need that information to figure out number 3. So, loss of bicarb. Or additional anion. What causes a loss of bicarb? Well, if you have GI losses or renal losses of your bicarb. GI losses, that's primarily diarrhea. Or renal losses, that's an RTA. I'll do another video on RTA at some point. Or also lumped into here is if you're adding chloride to the system, and so if you're giving normal saline. So we went over what causes a loss of bicarb, normal anion gap metabolic acidosis. What causes an elevated anion gap metabolic acidosis? The mnemonic I use is CULT. So, like maybe you're used to using mud piles, maybe you're used to using Goldmark. I like to use CULT. So K-U-L-T. What does K stand for? That's ketones. So you have an additional ketone, and that's what's lowering your bicarb. So ketones, that's your starvation ketoacidosis. Starvation keto. People on the keto diet, I feel like, are starving, so we'll leave it like that. You have your DKA, and then you also have your alcoholic ketoacidosis. What's U? So you have your uremic acids that also cause your anion gap metabolic acidosis. That's actually specifically primarily your phosphoric acid. If you're interested in that, it's not like you're measuring your phosphate and see it's elevated, but if you have an AKI, especially a prolonged AKI, that can cause a uremic acidosis. L, what does L stand for? Lactate. Honestly, it's probably going to be the majority of your high anion gap metabolic acidosis. T is toxins. I came up with a thing because there's so many toxins. I was like, how can you just say toxins and not tell me which one? This mnemonic doesn't help. So I came up with a thing to help us with the T in toxins. So there are 3 alcoholic toxins and 3 non-alcoholic toxins. My 3 alcoholic toxins are methanol, ethylene glycol, and propylene glycol. My 3 non-alcoholic toxins. Oh, and like if it helps, like I sometimes think MEP, if it helps you remember the alcoholic toxins. So 3 non-alcoholic toxins, there are 2 A's and an I. I don't know if that helps. Aspirin, acetaminophen, otherwise known as APAP. If APAP or acetaminophen, it actually causes pyroglutamic acidosis. The way you measure for it is measure an oxaproline level. If that's elevated, that indicates you have a Tylenol toxicity, or rather pyroglutamic acidosis from your Tylenol. The third one is INH or iron. There is a way to distinguish your alcoholic unmeasured anions from your non-alcoholic unmeasured anions. So, because like in case you haven't measured your labs yet, so at least in case you haven't measured your salicylic acid level yet or your Tylenol level, for example. Remember, alcohols aren't only unmeasured anions, they're also unmeasured osmoles. So that means that if you have an unmeasured, I guess you guys could hear that little toy in the background because my cat is playing with my baby's toy. Anyway, so if you have so these alcohols are unmeasured osmoles. That means there is an osmol gap. They don't only cause an anion gap metabolic acidosis, they also call it elevated osmol gap. So, how do you get an osmol gap? How do you calculate that? So here, you measure your serum osm, you just send it in the lab, and then you calculate it. And if there's a difference of more than 10, that difference must be accounted for by one of those alcoholic toxins. So the calculation for your osms is 2 times the sodium plus BUN divided by 2.8 plus glucose divided by 18. And then, if in case you happen to have any ethanol in the system, you also gotta account for that. Alcohol divided by 4. How do you remember this? Because this is a lot of numbers and it used to drive me insane. 2 times sodium, I don't have a great way of remembering that one, but BUN divided by 2.8. I can imagine like a normal BUN's like around 28. So I just think this BUN's around 28, I divide by 2.8. I don't know if that helps at all. Glucose, a normal glucose is like around 180. Okay, not normal. Inpatient maybe. Outpatient, you need to see a doctor if normally your glucose is around 180. You're maybe a little bit diabetic. So 28 divided by 2.8, 10, 180 divided by 18, 10. I don't know if that helps. It helps me. And a normal alcohol level should be 0 unless you're watching this drunk. And good job to those of you guys whose alcohol levels right now are 400 and you're dividing it by 4. And so you got to account for that. You got to account for that extra 100. It's important if your patient comes in drunk and you're also worried they have methanol in the system to factor this in, because sometimes people forget to factor this in and they get this huge osmol gap and they're like, oh my goodness, there must be so much of some toxic alcohol in the system. And they don't realize they forgot to factor this in. So they don't need to call poison control. Your patient's just drunk. If you do have a toxic alcohol in the system or you suspect it, you should be calling poison control. And renal as well, but half of you guys are renal, so call yourself. So we went through step 1 in analyzing a metabolic acidosis. We figured out if there's an additional respiratory acid disorder by using Winters. Number 2, we figured out what the cause of our metabolic acidosis is. Either it's a loss of bicarb with a normal anion gap or an additional anion, and that means there is an elevated anion gap. Remember to correct for albumin, and remember our mnemonic of COLT. Now, my third and final question is how to tell if there's an additional metabolic process, an additional metabolic acidosis or alkalosis. I don't know if you guys can hear my baby getting a little fussy in the background, or my husband's here, but maybe she's getting overwhelmed by how much. She's like, I got number 1 and number 2. There's a number 3. That's okay. That's okay, Celeste. We're getting through this. You got this. This is where delta comes in. I also have a separate video on delta, so if you watch that, you don't really have to pay attention to this point, but I'll go over it here. So, if you have an anion gap metabolic acidosis, remember I said that every time you added an anion, that unmeasured anion like your lactate, that's what lowers your bicarb. This means every time you have an extra anion, your bicarb decreases, and that's how you get that lower bicarb in your anion gap metabolic acidosis. So this means that every time my anion gap goes up by 1, every time I have additional unmeasured anion, that means my bicarb should go down by 1. So, if my anion gap, for example, was 11, saying a normal anion gap is 10, so my anion gap went up by 1 from normal, so I expect my bicarb to go down by 1 from normal. So my bicarb would go down by 1. So normal bicarb being about 24. So I expect my bicarb in this situation to be 23. Suppose I measure my anion gap. I calculate it, and I get an anion gap of 20. So my anion gap went up by 10. I have added an additional 10 anions. So that means I expect my expected bicarb should also go down by 10. So if a normal bicarb, or say, is 24, 25, so my expected bicarb is 24 minus 10, or 14. And then I look at my patient's levels, and I find out their actual bicarb is 10. It's lower than my expected bicarb. That means there's an additional metabolic acidosis, specifically an additional normal anion gap metabolic acidosis. This is a delta concept. So what delta is, and I go over this in another video too. What that ratio is that's your change in anion gap divided by a change in bicarb. This number should be about 1. If it's less than 1, they say, and I find this not as intuitive, they say that if it's less than 1, they say, that if there's an additional normal anion gap metabolic acidosis. If it's more than 2, it's an additional metabolic alkalosis. I like to say, the way I do it, I feel like it's more intuitive, so I just say the change in anion gap should be about the change in bicarb. If the bicarb's off from that, that's how you know that there's an additional process going on. Something to be said about your about the wiggle room you get with your delta. So your bicarb can actually be a little bit higher than the expected bicarb. So suppose my anion gap, so to explain what I mean by that, suppose my anion gap was 20. What's my expected bicarb? By the way, the way I do it, like expected bicarb, is it makes me think of how the Winters formula works. You calculate an expected PCO2. If the PCO2 is higher, there's additional respiratory acidosis. If it's lower, it's additional respiratory alkalosis. The way I think of delta is that I get an expected bicarb, and then if the bicarb's higher, is additional metabolic alkalosis. If it's lower, additional normal anion-gap metabolic acidosis. So expected bicarb here is gap went up by 10, so bicarb went down by 10, so it's about 14. If your actual bicarb is 13, additional normal anion-gap metabolic acidosis is lower than you expected. There's additional acidosis. If it's at 15, that doesn't automatically mean it's a metabolic alkalosis. Your bicarb can be a little higher than expected. How much higher? Specifically, half that change in your gap. So here, your expected bicarb is 14 to half that change in the gap, so 14 to 19. If you don't remember this, that's fine. You can still honestly analyze most of your acid-base disorders. So if your actual bicarb is 15, not a metabolic alkalosis. If your actual bicarb is 20, that is an additional metabolic alkalosis. There's no way to tell, using all these nice little cute formulas, if there's an additional anion-gap metabolic acidosis. The delta won't tell you that. It'll just be like, is some unmeasured anions that accounted for all of your metabolic acidosis, or it isn't. So, we actually just went over the hardest acid-base disorder, the metabolic acidosis, and how to tell if there's multiple issues going on there. The other ones aren't as bad. So suppose you have a patient whose pH is low as well. You have an acidemia. PCO2 is high. This is your respiratory acidosis. How do I tell if there's an additional metabolic process? In an acute respiratory acidosis, every time your PCO2 goes up by 10, your bicarb goes up by about 1. So I have an expected bicarb of going up by 1. If your actual bicarb is higher than that, there's an additional metabolic alkalosis. If it's lower than that, additional metabolic acidosis. This is for acute. For chronic respiratory acidosis, every time your PCO2 goes up by 10, your kidneys have a little more time to catch up, so your bicarb goes up by about 4. I've seen different numbers. I think Burden-Rose goes by 3.5, if I remember correctly. And Burden-Rose, you guys should read that. So in the situation of a respiratory alkalosis, pH here is high, you're alkalemic. PCO2 is low. In an acute process, it's about the same numbers. And if you don't remember the intricacies of what's different, you could probably just always go by 1 and 4. So every time your PCO2 goes down by 10, your bicarb goes down by 2. Every time you're in a chronic, every time your PCO2 goes down by 10, your bicarb goes down by about 4 as well. So here in that situation, you could also tell if there's an additional metabolic acidosis or alkalosis. At that point, I also look to see if there's an elevated anion gap, because there may be still more than one metabolic process. I might think, okay, my bicarb's lower than expected, it's just an additional metabolic acidosis. At that point, I still go back to this. Then I see, is there an anion gap? And so I figure out this additional anion gap metabolic acidosis. And then I figure out, is there an additional normal anion gap metabolic acidosis or alkalosis using delta. It's not generally normal to have an elevated anion gap. If you do, that pretty much always means you have an anion gap metabolic acidosis. So that's your respiratory issues. I don't know why I did respiratory before my metabolic alkalosis. So metabolic alkalosis, how do you analyze that? So you're alkalemic, your bicarb is elevated. So now I gotta figure out what my expected PCO2 is. So every time my bicarb goes up by 1, I expect my PCO2 to go up by 0.7. The PCO2 is higher than that, additional respiratory acidosis. If it's lower than that, additional respiratory alkalosis. Then also still look at your anion gap, because if there is an anion gap, there's got to be an additional elevated anion gap metabolic acidosis. So that should be everything. I'll probably go a little bit more into metabolic alkalosis and the respiratory issues in another video. One thing that's important to know is that you can only have one respiratory disorder at a time. Your lungs aren't that smart. Either you're holding on to CO2 or you're breathing it off. Your kidneys are a little more interesting and complex. You see what I did there, pulp crit people out there. So you can have you can have 3 metabolic processes at the same time. So you could have an anion gap metabolic acidosis and a normal anion gap metabolic acidosis and a metabolic alkalosis all at the same time. All right. I guess theoretically you can, but it might be a little hard to figure out with the delta. I had to think about that for a second. All right. Hope that helps. Message me if you have any questions.